Hello there, and in this video we're going to discuss and sort of investigate maybe one of the most common and most popular integrals across most of the calculus realm, and that is what people call the Gaussian integral. Now, if you're not familiar with the Gaussian integral, this definitely has several applications across various fields, including probability and statistics and also quantum mechanics. So what the integral says is, what is the integral under this function e to the minus x squared, where e to the minus squared is this bell curve shaped kind of curve. So what I'm going to begin with doing is I'm going to define this integral to be equal to I. Alright, so what we want to know is what is this area I equal to. So I'm going to begin by squaring this integral. So that's the same as, the integral from minus infinity to infinity of e to the minus squared dx minus, or times, the integral from minus infinity to infinity of e to the minus squared dx. So as you do notice, these two integrals are the same. And if I rotate this curve along the x-axis, so this curve would be e to the minus y squared, this area here would also be the same as the area underneath the other one. So what I can do is I can rewrite this as I squared is equal to the integral from minus infinity to infinity of e to the minus x squared dx times the integral from minus infinity to infinity of e to the minus y squared dy. Now, by Fubini's theorem in calculus, and if you're not familiar with that, maybe it's not important, but you may think that I can combine these integrals in the following way. I can rewrite this as the integral from minus infinity to infinity, or minus infinity to infinity, over e to the minus x squared times e to the minus y squared dx dy, which can be rewritten as the double integral of e to the minus x squared plus y squared dx dy. And since we're integrating from minus infinity to infinity in both the x and y directions, this integral covers all of R2, or two-dimensional space. So we've pretty much rewritten our single variable integral I as a volume integral I squared. Alright, so why would we want to do this? Well, you may observe that this x squared plus y squared is a familiar thing that you may have saw in trigonometry. So what we can do is we can let x squared plus y squared define to be equal to r squared. And I'm not going to prove it here, but you can verify it in some Calc 3 ways. That dx dy will be equal to r dr d theta. Alright, so if we take that as an assumption, we can rewrite this integral as follows. So I squared is going to be equal to the integral, or the double integral, e to the minus r squared times r dr d theta. And since we're pretty much covering all of R2 space across minus infinity to infinity here, we need to do this in terms of polar coordinates r and theta. So what we can do is we can sweep through this space in terms of circles, where the radius goes from 0 to infinity for r, and in terms of theta, we can rotate counterclockwise from 0 all the way out to 2 pi. That will complete the entire circle. So this integral, if r is on the inside, so r is going to range from 0 to infinity, and theta is going to range from 0 to 2 pi. Alright, great. So notice that this integral here does not have any thetas in it. So we can integrate with respect to theta because r is just going to be a constant, and that's going to be 2 pi minus 0, which is going to be equal to just 2 pi. So that means I squared is going to be equal to 2 pi times the integral from 0 to infinity of r e to the minus r squared dr. Alright, so if you're familiar with Calculus 2 methods, then this should be very straightforward. I'm going to use u substitution by letting u be equal to minus r squared. So if that is the case, then that means du is going to be equal to minus 2r dr. So dr is going to be equal to du divided by minus 2r. Also, I'm going to change my limits around. So when r is equal to 0 and when r is equal to infinity, what will my u be equal to? So when r is equal to 0, we get negative 0 squared, so that's going to be equal to 0. And when r is equal to infinity, infinity squared is super large, also infinity, with a minus sign in front of it. So we get our new integration bounds here. Alright, so that means I squared is going to be equal to 2 pi times the integral from 0 to minus infinity of what? So we have r times e to the u times du divided by minus 2r. Alright, so what do we have here? So we have a 2 and a 2 in the denominator, so they're going to eliminate. And we also have this negative sign that we can factor out. And also we have an r and an r that will cancel as well, which is why we use substitution. So we have I squared is equal to minus pi times the integral from 0 to negative infinity of e to the u du. And this is a very basic integral that you may even remember from Calculus 1. The integral from, or the antiderivative of e to the u is just going to be e to the u. So I can rewrite this as I squared is equal to minus pi times e to the u evaluated by the fundamental theorem of calculus from minus infinity down to 0. So as u goes to negative infinity, so if we know exponentials, as u gets close to negative infinity, this function is going to disappear and go to 0. And then as u gets close to 1, as u gets close to 0, exponentials are going to get close to 1. So 0 minus 1 is negative 1, and negative 1 times minus pi is going to be pi. So we have I squared is equal to positive pi. So that means I is equal to the square root of pi. Alright, but what is I? Well, I was the integral that we were originally interested in. So let us summarize what we have here. So that means the integral from minus infinity to infinity of e to the minus x squared dx is equal to the square root of pi. So this is the first result that we get from this. Now there are a couple other results that you may get from this as well. The second, since this function is symmetric about the y-axis, we can split this in half and question ourselves, what is the area under the curve from 0 to infinity? So by symmetry, that's just going to be half of the square root of pi. From here, I can divide both sides by the square root of pi over 2. So we can get that the integral from 0 to infinity of 2 divided by the square root of pi times e to the minus x squared dx, this is going to be equal to 1. Okay, well that's interesting. I guess you could say that. Now one could also verify from the first identity. So if the area under the curve from minus infinity to infinity of e to the minus squared dx, so 1 over the square root of pi times e to the minus squared dx, if this is equal to 1, then one can verify this very important property that has very, very many applications. Namely, the integral from minus infinity to infinity of 1 over the square root of 2 pi times e to the minus 1/2 x squared dx, that this also is equal to 1. And I leave it to you to verify that this implies this equation. And most people will recognize this equation. This is what we call the standard normal distribution, which is used in several applications in probability. So what we've done here is we proved that the standard normal distribution has area under the curve equal to 1, making it a probability distribution. But overall, the main purpose of this video was to prove that the integral from minus infinity to infinity of e to the minus x squared dx is going to be equal to the square root of pi. And this again is probably one of the most famous integrals that a lot of mathematicians tend to do as a practice problem, sometimes even an exam problem in some higher level calculus courses. But that's pretty much it.